Welcome engineering statics students. This mini lecture will cover topics in inertial properties of plane areas, otherwise known as moment of inertia. So I will jump right into explaining this topic from the point of view of some instructor hand-constructed notes drawn from some excellent textbooks, and the aim here is to convey to you the real essential characteristics of moment of inertia, how you can combine moment of inertia around different axes, create a polar moment of inertia, looking at a third axis from the one that your plane area is contained in, and then follow up with the method of composite areas, which is an analog to the method of composite parts for centroid. Speaking of centroid, you're going to find a lot of analogs to your study and derivation of centroid in terms of its definition of a moment, of a given bit of length, area, or volume around a certain axis divided by the overall volume or area or length of your line, area, or body, respectively. And the only difference here is rather than looking at a moment calculation in the numerator of our definition, we're going to be looking at something with a squared radius known as the second moment. So I will dive right into it here with the notes. So inertial properties of plane areas. So over here on the left we have a coordinate system, x and y, plane coordinates. So our z-axis or k-hat axis would be pointing out of the screen towards us. And the origin of that is point P. And the figure is a little bit faint, apologies, but we've got a little differential area, bit of area somewhere in this overall body. And it's located at coordinate x in the x-axis and y in the y-axis. So here's some dimensions given. So that's how far this little area bit is from the actual coordinate axes x and y, or our I-hat and j-hat axes. So we would define the moments of inertia of the whole plane area with respect to either the x-axis, and that's I sub x, so moment of inertia with respect to the x-axis is a capital I with a subscript x, or with respect to the y-axis, capital I with a subscript y as two different integrals. So if I want the moment of inertia of this body around the x-axis, and notice I'm revolving my pointer as if I'm spinning around the x-axis. So moment of inertia is inextricably linked with the concept of rotation. Just like centroid could be thought of as the balance point, that if you took your body and put it into a gravitational field, what is the one point, assuming uniform density of course, that you could balance that whole body on so it wouldn't tip over? When we look at moment of inertia, what we're looking at is more or less how much area or volume or length, if it's like just a hoop or something, is located how far from an axis of rotation. So the concept of rotation and the concept of moment of inertia are kind of tied into one another qualitatively, so to speak. So if I'm going to rotate this body around the x-axis, I would define the moment of inertia around that x-axis as the integral over the whole body of y squared, which just so happens to be the distance, perpendicular distance from that little bit of area from the x-axis. Hey, like an r from an axis of rotation for moment calculation, same exact concept. And then I'm going to sum this up over all of the differential area bits. So I have an integral over a of y squared dA defines moment of inertia with respect to the x-axis. I'm going to add up all the bits of area, and I'm going to multiply each area bit by how far that bit is from the x-axis squared. So no negative terms. That length is always squared, so it's always going to be a positive number. Likewise, if I want to look at spinning this bit of area around the y-axis, I've got the same considerations, except now my radius vector, so to speak, from that y-axis to wherever this bit of area is located, that distance is now defined as the x-coordinate. So now I have x squared dA. So the squared term here is very analogous to the linear term in our moment expression that we use to define centroid. In fact, if we had, instead of a squared term, if we had a linear term in each of these two, and then we divided by the entire area, we would have the centroid. So if you think about the power of this sort of radius term within this integral, and look at the fact that centroid, this was raised for a centroid calculation. We had an integral expression that had this term raised to the first power. You could think of centroid as being the first moment, so to speak, and moment of inertia, having a squared term, is known in some places as the second moment of, in this case, area. If we were defining this for a 3D body, it would be the second moment of volume. If we were defining it for some linear wire body or hoop, it would be the second moment of the line or the path or whatever the 1D type of body where we're looking at. So second moment, squared term, moment of inertia, all means the same thing. Okay, and the physical implication again is how much of the area or volume or length, depending on what dimension of body you're talking about, is located how far from a line, and that you can think of as the line of rotation, your axis of rotation. So we're going to do an example with a body we're probably all pretty familiar with. We have a triangle here, and it has a height of h, and it has a base, which is up here at the y-axis at a higher y value, and then the point. So it's a bit of an inverted triangle. So we have base height defining the triangle dimensions, and we want to know the moment of inertia about the y-axis. So how much of this triangle is located how far from our y-axis? So just like we did with centroid, the key to moment of inertia is, not surprisingly, finding a differential area unit, in this case being 2D, in which every bit of that area unit, differential volume, or excuse me, differential area, is at the same x distance from our y-axis, because we're going to integrate with respect to x. So the differential slice has to all be at the same distance from our axis of rotation. So we've defined the differential area shaded, so it's going to have a width of dx, which is great because we're going to integrate with respect to x, and then it's got its own height equal to h minus whatever the x value of this effective diagonal line going here. So if I can write a line equation for this line that defines the base of that, or excuse me, the bottom end of that triangle, I can substitute that for y, and then I can write a height of my area strip in terms of a function that relates to the dimensions of the triangle. So that's what I've got right here. So I can define my differential area as h minus y dx, but I want to express y in terms of x, so I can integrate more easily with respect to x in my moment integral. So I make a line equation relating y to x based on the dimensions of the triangle and substitute that for y. Now I've got my differential area. Now I can substitute that right in to my integral and include my x squared, so since I'm calculating moment of inertia. And then I'm gonna take advantage in this case of some symmetry. The triangle is symmetric about the y-axis, so instead of having to do a piecewise integral from negative b over 2 with a line with a negative slope, and then add to that a second integral with our positive slope line that we just defined, I'm just going to do one side of the triangle and multiply by 2, because that's going to give me the same answer. So I'm using the symmetry of the area of the triangle, and so I'm going to integrate from 0 to b over 2, multiply by 2, and when I do that, I get this expression For the integrated expression, I can substitute in my lower and upper limits of integration, and I get the height of the triangle times the base cubed, in this case over 48. And you'll notice we've defined our area moment of inertia in terms of a fourth power of length. So if this were meters, it would be meters to the fourth, inches to the fourth, whatever length unit we're in. Again, if we had not used symmetry, we would have had to have integrated over the whole body. So just be careful when you have something symmetric there. Okay, so we've got an idea about how to define moment of inertia around an x-axis, a y-axis, or a z-axis for planar bodies. We can basically take a slice and define an area moment around whatever axis. What if we want to look at an area and then revolve it around the origin itself, presumably around an axis that's coming out of the page here? So if we look at this figure here in the upper left, what if we wanted to take this body that we've defined, it's a little faint, and rather than looking at rotating it around the x or the y-axis, we want to kind of rotate it around what would be the z-axis coming out of the page. So now the distance of this body being rotated around the z-axis is not defined by its x or y coordinates, but by r. So now we're kind of in an r theta world, and so that's why it's called the polar moment of inertia, because now our distance is a radius that is related to x and y position of a coordinate system by Pythagorean, which is super convenient for us. So we can just invoke the general concept of a moment of inertia of our area, a differential area at a known distance from perpendicular distance from the axis of rotation, integrated over the whole area. Okay, so in this case, the only difference from what we defined for our I sub x and I sub y is that we've got an r instead of an x or a y coordinate. So this J sub p is a convention that's typically used for the polar moment of inertia. And so you can think about that as just being maybe the moment of inertia around the z-axis in a polar coordinate system, so like a cylindrical symmetric system. In this case, the cylinder would be, cross-section would be here in the page, and we're looking at rotating things around the axis of a cylinder coming out of the screen. Well, a nice relationship here is that we can use Pythagorean theorem to relate r to x and y. So I can just substitute r squared plus y squared, or excuse me, x squared plus y squared for r squared, because of course we have this right triangle relationship. And then I can use the properties of integrals, that the integral of a sum is the sum of the integrals, and relate the polar moment of inertia to the sum of the single axis moment of inertias that we just described. So if you have already calculated your I sub x and your I sub y, and then you want to look at what the moment of inertia of that same body would be if you swung it around the axis perpendicular to the two you've already defined, all I have to do is add them up. That's very, very convenient. This action here is a little bit of a glimpse ahead towards what's called the parallel axis theorem, where we look at moving our consideration of which axis we're rotating around from one where we know the moment of inertia to another where maybe we don't. So we're shifting the axis in a way, except this time we're shifting it not a distance in plane, but we're shifting it to something that's perpendicular to the other two. Okay, so here's a classic example. Let's take a ring or a disc. So it doesn't get much more polar than a circle. So we're going to define our circular area element right here, and we're going to put it at a radius r, and we want to know what the polar moment of inertia of an entire circle, so like a disc, a filled-in circle, not just a hoop. So here's a close-up of our area unit, and I started by defining it as an area with a little thickness. So we got a delta r just to show it a little easier. So we've got we've got a bit of radius, a delta r, and then we've subtended a delta theta angle. And we can define the area in terms of an average between these two different side lengths, because we've got an r plus delta r and an r here. And so we can use our, basically add up the dimensions of the rectangle and multiply an average length times delta r to get area. So we could say our average length or height in the delta s direction, so to speak, circumferential, would be our r delta theta plus r plus r delta theta. It should be an r plus r, and then half of that delta r. In fact, I will do that. There should be delta r. So here's your r plus delta r, and then here's your r. So we've defined an average height that goes down the middle. And then, of course, our direction dimension is delta r. A little wordy there. But if I shrink all of that down using a differential expression for theta and r, so if I shrink delta theta down to d theta and I shrink delta r down to dr, I get my r dr d theta as the differential area expression in polar coordinates, which you probably recognize if you review your calculus a little bit. So our differential area unit is r d theta dr, and we can pop that in right here for area, and then we've got our distance of that from our axis of rotation at the middle, which is just r squared. So we end up integrating r cubed dr d theta. And the nice thing is now we're in a position to define the polar moment of inertia of the whole circular disk, a ring that goes around it, or even a little pie-shaped wedge, or even some arced area unit, depending on how far we want to integrate around d theta and how far we want to integrate out and over what interval. Do we want to integrate all the way from the middle and get a disk? Do we want to integrate from one r to another and get some kind of ring? Simply by adjusting our limits of integration, we can get a whole circle, a pie, a ring, or any bit of those. So in this case, we want the whole disk. So we're going to integrate all the way around the circle from 0 to 2 theta, and we're going to integrate from the center of the circle all the way out to capital R, which defines the circle disk radius that we were concerned with. So integral with respect to theta of something that has no theta in it is just going to be the integral of a constant. So we end up getting a d theta for our first integral, and now we're going to integrate with respect to r. We're going to end up with, of course, integral of r cubed is 1/4 r to the 4th, and so 1/4 times 2 pi is pi over 2, and then we have our limits of integration of 0 to r, and we get pi over 2 r to the 4th, and once again we've got our 4th power of a length defining a moment of inertia. So we've got consistent units, which is very reassuring. Okay. Again, what if we need another axis? Because in case you haven't noticed, all of our examples so far have included something being rotated around an axis that looks an awful lot like it's going through the centroid, or assuming it's uniform density, the center of mass. So a lot of times we want to rotate something around something that isn't the center of mass. So we can always define a radius. So let's contextualize things to this example here in this drawing. So we've got a body that has a centroid at point C. So to this point, we would have defined moments of inertia as being with respect to this point. So either we're going to rotate around the x-axis and we'll look at the y-coordinate of our area, or we're going to rotate around the y-axis, so we'd look at the x-coordinate of this area, or we're going to rotate around point C around an axis coming out of the paper, and so we would look at the radial component, the r between C and dA. So we've covered that so far in our examples. But what if we're going to take this whole body and we're going to rotate it around point P way over here, which is not the centroid of that body? Okay. Typically, we will have already defined in a lot of cases the moment of inertia around the centroid with respect to both axes and maybe the polar moment of inertia as well. We did this for a triangle, we did it for a circle. You'll find as you go on in your studies, there's lookup tables for standard shapes where somebody has already done the integration and then wrote down the results in terms of the dimensions of your shape and which axis you're talking about. So those are look-upable, or you can do the integral, and they tend to be pretty simple because you're not working with funky shapes and crazy integration limits, or more importantly, complicated expressions for just how far is that bit of area from the particular axis I care about. It might be kind of difficult to envision a continuous function that describes that distance, which is kind of the essential part of the moment of inertia expression, that distance squared. So in a lot of cases, it's a lot easier to look at ways to adapt the moment of inertia for a centroid or for a body about an axis that runs through its centroid to its moment of inertia about some other point. So we're going to step through the derivation of that expression so it makes some sense, and what we will end up with is something called the parallel axis theorem, and then we're just going to use it, which is kind of fun. Both are fun. So we got our body. It's floating around out here. It's got a centroid at point C, and we can define the distance in the y and x direction of a little area, differential area unit, in terms of the centroid as y sub c and x sub c. Now we're gonna scan out, and we're gonna look at where this body is sitting with respect to a larger coordinate system, a different reference frame, so to speak. So we've got point P at the origin of this other reference frame, and we're going to describe the y and x axes of this other coordinate system as x sub p and y sub p. So we can define a couple of really important distances for moment of inertia in terms of this bigger reference frame. One is going to be a y bar, which is the y centroid of this body with respect to P. So remember, the over bar is the location of the centroid of a body from a given coordinate axis. So x bar and y bar says, how far is the centroid of this body from my coordinate system P? Okay, kind of important. And now we can also define how far any point, this area point is from the origin in terms of how far is it from the centroid, and then how far is the centroid from P. So we can now define moment of inertia of this body around P in terms of a summation distance. So we'll set that up here. So if I were just to write, say, the moment of inertia around x sub p, so the moment of inertia of this body around this axis, this x sub p, x-axis with respect to point P, I just have the total distance of this area from x sub p. So that would be y sub p coordinate. So the y coordinate with respect to P at the origin. So we'll call that y sub p, and we would integrate the distance y sub p squared over the entire area, with respect to our area unit. And the same with the moment of inertia of this body around the y-axis. We just integrate the distance, the x distance in our P coordinate system over the whole area. But we can define y sub p and x sub p as a sum, each one of them, of the distance of the centroid from the axis and then the distance of the area unit from the centroid, because they all add up to y or x sub p. And then we can pop those into the integrals and rearrange them and see what we got. So again, express y sub p and x sub p in terms of distance that the centroid of our body is from the p coordinate system, or from the p origin, and then the distance of our area, our differential area, from the centroid of the body. So distance of our area from p in the y direction is y centroid location plus y sub c. Distance of our differential area from p in the x direction is x centroid plus x sub c. So just a sum. And we would have another corresponding distance in z sub p if we were looking at that. So we can just plop those sums into our expressions for moment of inertia for both x and y, and then we'll go ahead and expand out those squared terms, and we end up with basically the integral of a sum of 3 terms. And now we're going to invoke the integral of a sum as the sum of the integrals, and we're going to write those as the sum of 3 integrals, and then see if we can recognize something useful about each of those terms that we can run away with and create the method of the parallel axis theorem. So the first thing we were going to notice is that y bar is a single number. This is effectively a constant. It's not changing as we're integrating over the area. That centroid stays fixed. It is what it is with respect to any external coordinate system. It's really the y sub c, the distance of the differential area unit from the centroid, is the only term that's changing. So we can take the y bar outside of the integral anytime it appears. So we start with our first term, where we have just y bar squared dA. And if we look at y bar squared, what we notice is that is the distance, and we'll go back to our figure, that's the distance of the centroid from the new axis. So if we were to look at, here's where we get parallel axis, right? If we look at the x-axis through the centroid, which just so happens to be parallel to the x-axis through point P, the distance between the two parallel axes is the y-centroid location, y bar. Hey, pretty cool. And let's go back to our integral. So we have the distance between the two parallel axes. We'll call that d1 squared. And then that's being multiplied by the integral over the whole area of an area differential, which is the area. So we've got this expression, the distance between the two axes, the centroid axis and the parallel to that centroid axis that we're considering, squared times the body area. Okay, cool. There's one term. We can define that for a shape. So that's pretty handy. So let's look at this middle term, which looks kind of squirrely. So we've got twice the centroid location, so that's going to be a number. Then we have the integral over the whole area of the y-centroid with respect to that area unit. Now, if you go back and you look up the definition of the y-centroid, you'll find that this is actually 0 by definition, as part of the definition of centroid, as the point at which the distance from that point all around the area is the same in every direction, so they effectively all cancel out. So this middle term is a 0 by definition of the concept of a centroid. And last but not least, we've got the moment of inertia about the x-axis that goes through the centroid. We've got y sub c, so that's the distance of our area unit from the x-axis through the centroid. So this is our moment of inertia about the x point through the centroid. So what we end up with is an expression that says the moment of inertia about, in this case, the x-axis through any point, anywhere, is the moment of inertia about the x-axis through the centroid, probably easier to calculate and or look up, plus the square of the distance of my proposed new axis from the centroid axis times the area. And we can create a corresponding formula for the moment of inertia around the y-axis through any point. So these two expressions are the parallel axis theorem for the x and y axes. So we can it's also known as the transfer theorem, because you are transferring that moment of inertia from an axis that goes through the centroid to an axis that goes parallel to it, that goes through anything else. So notice, because these terms are squared, you don't have negative area, you have a distance squared, this term's always positive. So this is also kind of an interesting idea that the moment of inertia about an axis that goes through the centroid is the smallest moment of inertia that you can get. So Ix through any point or Iy through any point is always going to be more than that same moment of inertia if we put it through the centroid. So that's another kind of by observation trend that you can see that comes out of the parallel axis theorem. So if you're looking for a place to rotate and you for whatever reason need to minimize moment of inertia, try to rotate about the centroid. So we have a quick example of this. We've got our circle, and here's its centroid right in the middle. Again, centroid as opposed to center of mass, it would be the same if this had uniform density. And you've got some distance L from the upper radius of that circle to point P, and rather than rotating about the centroid, somebody wants to know what is the moment of inertia in both the x and the y directions, or about the x and y axes, through P instead of C. And the nice thing is we've already defined the moment of inertia, the polar moment of inertia for a circle, and we know that a circle is symmetric, so we can go back to our scrolling back here. This result, we can invoke this part of the definition of polar moment of inertia and be pretty darn sure that the moment of inertia about the x and y axes of a circle is going to be pi over 4 r to the 4th. So we now have this term and this term. Oops, sorry. And that one. Basically, so all we have to do if we want to get the moment of inertia about point P is find how far point P is in the y direction and x direction from the centroid and the area of the circle. So we don't have to get some complicated integral where we define some kind of crazy strip over here and figure out how far it is from P. We could do that if we wanted to do a lot of math, but it's a lot easier to use the parallel axis theorem because there's a lot more options. Even if we didn't already have a formula that we had pre-derived for the moment of inertia about both axes through the centroid of our shape, it's usually easier to do the integration around the centroid. Just the mathematical expressions tend to be a little bit easier. So either way, we're golden. So if we're looking for the moment of inertia about the y-axis that goes through point P, well, the first thing to notice is the y-axis that goes through point P is the same y-axis that goes through point C. So the distance between those two axes is 0. So there is no difference. So around the y-axis, the moment of inertia in the y direction, or around the y-axis through point P and point C, are the same. But if we're looking at the moment of inertia about the x-axis, we're going to get a big difference, because in this case our offset between those two parallel axes, our y bar in this case is going to be pretty big. It's going to be r plus L, that's going to be squared. And so that will be added to our pi over 4 r to the fourth. And again, I didn't multiply these out, but you'll notice you've got linear term squared, or excuse me, length term squared, and the length term squared is going to give us a length term to the fourth, which is what we would need for Ix sub p. And so if we drop in all of our values, we end up with, again, this expression for the x-axis moment of inertia through point P, and then through point P again, and the y is the same as through the centroid. So there's a quick parallel axis theorem. Okay, we all remember, hopefully, method of composite parts for defining centroid, and it again leverages the fact that the integral of the sum is the sum of the integrals. So we have an analogous kind of relationship for moment of inertia, where if we look at an entire area, and I'm just glancing down here into our example, for instance, we've got this kind of complicated shape. If we want to know what the moment of inertia of this shape is around point C, we can use the fact that this shape itself is the sum of all of these areas, each of which will have its own relationship of distance to point C. And if we were to sum those distances and areas within this integral, we would end up with an integral of a summation term over that whole area, which we could then break up pretty much the way we did when we defined polar moment of inertia in terms of x and y moments of inertia. And we would get something like this. We would end up with the y squared distance to whatever area we were concerned with, maybe a sub area, and we would integrate that over that sub area, and then another sub area and another sub area, where A1, A2, and A3 sub areas added up to a total. We could break that moment of inertia integral up into 3 integrals, each of which would themselves define a moment of inertia for this sub area. So if it happened to be a lot easier to define the moment of inertia of each of those sub areas, say they were circles or rectangles or something that you already knew the moment of inertia formula for, or could integrate it very, very easily, you could simply define those, then know what the actual area was, ratio, integrate over just that area, and then add them up. Again, moment of inertia is always additive, nothing's subtracting. So again, this is not a balance around a given point, it's total area or volume or length, depending on what dimension you're in, from a given rotation axis. That's where that squared term is coming in. So the moment of inertia of the total equals the sum of the moment of inertia of all of the composite parts. So given that we're looking at area moment of inertia, this is the method of composite areas. So here's a quick example. We have a channel beam. This is something very, very typical that you would use for buildings or any kind of structures. And it's got a centroid somewhere in the middle, basically. We don't know how far it is in the x direction. We're not concerned because we're not looking at the y-axis moment of inertia. We're only looking at the x-axis. So we're only concerned with how far all of the area of this beam is from x sub c, from the x-axis going through the centroid. So if we were to define some kind of function for area, it might get kind of complicated. We'd have to do a piecewise integral, which would land us back at the integral of some complicated sum. Or we could go straight for the sum of the integrals and say, well, I've basically got 3 rectangles. I've got rectangle B, A, and C, and I can define the moment of inertia about this axis, x sub c, for each one. And in the case of B and C, I'm actually going to use the parallel axis theorem as well. because I have already defined, or could look up easily, a formula for the moment of inertia of a rectangle about an axis going basically straight through through its centroid in the x or the y. So that's what I'm going to start with. I'm going to look for the moment of inertia of rectangle B about x sub c, and to do that I'm going to define an axis through the centroid of rectangle B as x sub 1 here. So to get the moment of inertia of rectangle B up here on the top about x sub c, I'm going to use the method of composite parts and express that as the sum of the moment of inertia of rectangle B about its own centroid, which happens to be x sub 1, x-axis centroid, times the area of rectangle B times the distance between x sub 1 and x sub c, which in this case happens to be 2.75 inches. So there's the method of composite parts to get 1/3 of what's going to be my total moment of inertia for the whole channel beam. And by symmetry, B and C are equidistant from x sub c. They're the same area, same shape. So I got 2 of the 3 rectangles, and then now I can just rotate rectangle A basically about the x-axis, which happens to go through its centroid, so I don't have to use the method of composite parts. And so I just invoke the centroid, or excuse me, the moment of inertia about an axis, the x-axis through the centroid of a rectangle, and get a value for that. And now I add up all of them. So I have 2 times my I sub b through about x sub c, 1 for B and 1 for C, and then add that the moment of inertia for rectangle A to get the whole channel beam about x sub c, and find something that's larger than any of the component parts. So basically notice just to compare some terms here. So we're looking at basically the total area distant from x sub c. Notice that the value for B and C, even though these were smaller rectangles, their moment of inertia about x was much bigger because of this parallel axis offset, this 2.75 inch term here. So if you wanted to increase the moment of inertia of this channel beam about x sub c without adding a whole lot of material, you might just want to increase A only and maintain the same area in B and C and just put them further away. So that's the concept of moment, same amount further away, same force, longer r, bigger r, which is probably why the term moment comes into these definitions. Second moment of inertia. So that is it for this lecture. So we have now covered the essential parts of moment of inertia for statics, definitions, comparison to centroid, polar versus single axis, method of parallel axis theorem, and method of composite areas. So just a word looking ahead. Places you'll deploy moment of inertia. You may be encountering this at the very end of a statics course. And that's why I've titled this as for statics students. You may also be running across this as one of the early concepts in a dynamics course because of the implications for rotation. Moment of inertia is fundamental for the study of dynamics in that it ends up being front and center in Newton's second law application for rotating bodies. So it's the rotating M, so to speak. So if you're in dynamics, your F equals ma will have a rotational analog of torque, or tau, equaling alpha, or the rotational acceleration times I, the moment of inertia about your rotation axis, which is the inertial or mass type of component to your Newton's second law in dynamics for rotating bodies. So you will definitely see it there. And if you are a strengths and materials or mechanics of materials student and you are looking at designing beams or other flexing and twisting types of structures, moment of inertia will come into your flexural and torsional properties of certain types of beams and column structures. So you'll definitely see moment of inertia again in both of those courses, but know how it relates to the concept of the centroid, which is useful in all courses, including statics.